Hello everyone, I'm Sasi. I work as a data privacy researcher at Privitar, and this is my first Flower event. And I have been speaking to some of the Flower Labs guys, and it's great to see the progress in this community. And I learned that the community is growing exponentially. Hopefully, I'll be able to contribute and be part of the future Flower events as well. You are doing great work, and Privitar as a company and I as a person, I'm very interested in federated analysis, and hopefully, Flower will play a key part of our life in the future. And that said, as the title says, I'll be talking about privacy preserving federated analytics for financial crime detection. There's a solution we developed for the Pets Prize Challenge. And thanks, Ray, for the amazing talk and also stealing my thunder because you gave away a lot of the details. And for this project, we partnered with UCL and Cardiff University. As you can see, Professor Stephen Murdoch from UCL is already in the audience. And if you have any difficult questions, please get in touch with him. Please ask me only the simple questions. And from the Privitar Labs team, I also want to highlight Jack and Francesco, who are research engineers in the Labs team. They were planning to be here, but unfortunately couldn't make it. And I'm sure they could have given better responses about any questions related to Flower, but I'll try to fill in. And with that said, let me go to the problem statement. I know Dave has already covered a bit about the actual problem statement, but let me rephrase it so that I can position our solution in the context. So the problem statement, we participated in the financial crime track, and the goal there is to build an anomaly detection model. And we have like Swift and the different banks containing two different types of information that when pooled together can lead to better anomaly detection models. The idea is Swift is this secure financial messaging service provider. So they have details about who is the sender, who is the recipient, and what should the transaction be. But they lack intricate details about what the account is. For example, when was the account opened and does the account correspond to a deceased person and so on, which only the banks know. And the hypothesis is if they can both work together, they'll be able to build better anomaly detection models. And as with any finance companies, there are so many regulations around sharing the data directly. So they wanted to try a federated learning solution. And something interesting about this problem statement is it's both cross silo and cross device, because we have banks that contain similar information about an account, and there are multiple such banks. And we have Swift that contains information that's specific to a transaction. So it's cross silo because Swift has some information about a transaction and the corresponding banks have complementary information. And it's cross device because we have multiple banks that have similar information, but about different people and different accounts. And we found the challenge quite interesting because it's a mix of all these, and we can develop state-of-art solutions. And as mentioned by Dave earlier, we used all this mix of techniques to develop our end-to-end solution at the appropriate places, which I'll show in the architecture now. I know there is a lot there, but let me break that down initially. So our solution has three layers. You can imagine it in three layers. The first is the data layer, where the holy grail principle of federated learning is now no plain text data from the data layer is explicitly shared with any parties. So raw data stays at each of the institutions. And on top of the data layer, we have the feature extraction layer, which is the first step in most machine learning tasks. And even in the features, we could imagine different types of features. For example, Swift has labels of anomaly, what's an anomaly transaction, whereas the banks don't. So Swift could extract features from just its own data and learn a machine learning model. And if needed, it can add a privacy protection. That's one type of feature where you have the labels, you can extract the features and train your own model. And the second type of features are features that the banks contain. For example, some flags indicating whether the account is suspicious or not. And these features should be shared with some server, or they should be engaged in a machine learning task because banks don't have a label to learn a model. So that's the second type of features for which we use local differential privacy, because banks don't trust anyone to share this information. And the third type of features, which are the most exciting, are joint features, in the sense that you need data from multiple institutions to compute these features. And I'll explain more about the what joint features we have computed and why we used PSI. But then let me go to the next part, which is the machine learning part. Once we have the features coming from different institutions, we had two different parties: the active party, which is Swift in this case because it has the labels of which transaction is an anomalous one, and the passive party, which is the server in our Flower setup that has features extracted from banks as well as the joint features. And now the problem boils down to a classic vertical partition or cross silo federated learning with two parties, because the features are only distributed with Swift and the passive party. So we have converted this both cross silo and cross device problem into a classic cross silo problem. And we use secure gradient boost, but any model can be used. And the only reason we use secure gradient boost was in Kaggle, a lot of financial tasks were owned by more people who use gradient boost. So we just used a secure version of it. But people in the audience and a lot of people working on Flower are way more experts on federated learning. So I'll skip that part, but I'll talk about a complementary aspect of federated learning later on. But for now, let me go to the two aspects of joint features and local differential privacy, which I think are interesting. So the joint feature that I mentioned is called account discrepancy feature, where the idea is very simple. In a transaction, you have two accounts, the sender account and the receiver account. And and if there is a difference between the names or addresses or even the street corresponding to the account in corresponding to the information at Swift versus the actual bank that has this account, it's a clear red flag because you are telling something that's different. And we observed that even in the data set that we got, whenever there is this mismatch between either the beneficiary details or the recipient details, it is highly likely to be an anomalous transaction. The twist here is if the banks and Swift could directly compare the names in plain text, they could easily get this feature. But unfortunately, names and this is all personal information, so they could not compute the similarity or discrepancy in plain text. And as I wrote there, the challenge is if there is no match, it's a clear indication that something is going on. But if there is a no match, we also don't want any party to learn anything about what the difference is. Or let's say instead of Sasi, the name was Rahul, or instead of Rahul, the name was Sachin. We don't know. But the idea is to not disclose the names, but also gather this discrepancy features. And we found private set intersection to be a cool solution for this, because there are like very mature and scalable private set intersection protocols. And it's an interesting application because generally private set intersection protocols are applied to find how many intersections exist between two sets, or like what are the intersection values. But we used it to generate these discrepancy features, and Swift and banks exchange these encrypted messages tied to transaction ID, which can be tokenized or replaced with some random ID. And you have the bank account corresponding to a bank account, as well as the corresponding information such as name, street, city, country, zip, and we encoded some other features. And it's just a 0-1 flag, one for the sender and one for the receiver. So for every transaction, Swift can engage in a PSI with the two banks to figure out the 0-1 flags for the sender or the receiver. And the idea is neither Swift nor the banks will learn plain text details of these personal information, and the server will never learn anything associated with the personal information, because all it receives is a token that's an ID for a transaction and 0-1 values for the sender and recipient accounts. And this was one of the primary boosters for our accuracy from just a Swift alone model versus the federated model, because we have this additional feature. The second feature that we added for improving accuracy in the federated setting are the flag values, which are present only at the banks. And these are sensitive information that couldn't be shared in plain text form, because the flags could correspond to the account correspond to a deceased person, or they weren't doing transactions in the past few years in active account and so on. And it clearly seemed like a great application of local differential privacy. And what we did was we correspond for every transaction that's at Swift, we located the corresponding bank account, and the bank would share the flag values, but only after applying a privacy mechanism, which I tried to represent something like orbitals in chemistry, but it didn't quite really work. But the idea is you can flip some zeros to ones, some ones to zeros. And given this obfuscation mechanism, it provides some privacy guarantees. And the creative part is how do you pick this privacy mechanism that provides enough obfuscation, but also doesn't destroy the utility. That's where one of the key innovation for us in the project comes in, finding optimal privacy mechanisms as a flag protection game. The idea is to simulate banks and an simulated adversary where banks try to obfuscate the flags under some constraints of utility, saying, I want to protect, maybe I want to not flip more than 10% of the flags, or I don't want to destroy my utility by X percentage. And given these constraints, what are all the privacy mechanisms that I can use? The simulated adversary knows these privacy mechanisms, and they try to apply an inference mechanism. And when we phrase this game as an optimization problem, it boils down to a cute formulation which can be solved by linear programming to find the optimal privacy mechanisms. And what helped us in formulating it this way is the traditional way to use local differential privacy is to use mechanisms like randomized response or use Laplace noise, but then do some post processing and so on. So those are all like closed form solutions. Whereas when you formulate it as a game like this, you can explore the entire privacy mechanism space. And I think like the previous speaker, Tian mentioned, you can define relaxed versions of privacy definitions, need not be local differential privacy, but you can create a privacy, you can create a definition where your privacy definition is based on how accurately could this simulated adversary reconstruct the flag values. And we tried these different definitions of privacy and explored the privacy space to figure out the best privacy mechanisms. And in the process, we also found some cool open problems at the intersection of finding mechanisms for local differential privacy and using linear programs to solve that gap. So if you are working on differential privacy, please come and talk to me later. And I think we have some cool problems in this space. The next part of the talk is going to be slightly different from the traditional talks we have seen till now, which are mostly focused on cross-device federated learning and are quite technical. But this part is going to be focused on cross-silo and extremely non-technical, because the challenge was cool, it was fun. But at the end of the day, Privitar is a product company, and we are focused on bringing in advanced privacy technologies into the market to solve real world use cases. So before we go into like thinking about how to build a product around federated learning, let's just look at what an ideal product should satisfy for privacy engineering in practice. The first feature is trustworthy. By trustworthy, I mean people or organizations should be able to trust your software with their sensitive data, because you are saying you will protect their sensitive information. The rest of the four features are very important for any enterprise software, but trustworthiness is like the core focus for any privacy company or even security. And the second is intuitive. Anybody who tried to explain differential privacy to somebody who is not in the domain will know the importance of why intuitive techniques or why intuitive technologies are necessary for adaptation. And in fact, as Daniel mentioned today morning, the hypothesis for Flower is the simpler it is, the more adaptable it's going to be, the more adoption we are going to see. And I really loved it because working in the privacy space for more than 3-4 years, I can say that even k-anonymity or providing any tunable parameters to people who are not experts is only going to destroy the adoption of the product. So it's really important to ensure that whatever complicated technique that we are building is hidden under a very intuitive interface. And the third is reusable. I think Dave covered this earlier, which is it's very easy to build bespoke solutions in privacy tech, where especially multi-party computation, secure multi-party computation is a great example of this. You can build one solution for a niche use case, but it's not reusable at any other use case or even at other organizations. So it's not a product that you can repeatedly sell. So, and the fourth part is interoperability. When you are selling to enterprise softwares, they already have like different stacks and it's a huge mess. So unless you are willing to play in this mess, they won't buy it. Even if you are solving the coolest problem or you have great tech, the first question they're going to ask is, will it integrate with my existing systems? And the last, well, most underappreciated part in the tech community is most products need to fit into the organization's people and processes, in the sense that people who are going to use your product and also the procedures that are in place for sharing data inside the organization. In fact, I'll delve into more detail in the about the people and process part later on. But the great thing about the PETS Prize challenge was it helped advance these three aspects that I highlighted extremely well in federated learning, because with the trustworthy aspect, the PETS Prize challenge helped progress these three aspects, because with the trustworthy aspect, we had red teamings evaluate our solutions. And intuitive, it's still they tried to do something around explainable solutions. There was some progress, but not as much as the trustworthy or the reusable aspect. And one example of the reusable aspect is the secure aggregation solution, which I think the home winning team under Professor Nicola Helene's lab was also using. And we have seen that solution around a lot of teams. But what it couldn't contribute to is this two aspects, the interoperability and for people and process. Of course, a challenge can't do anything and it's limited to the scope. But at Privitar, we have identified this problem as really important, and Privitar's data security platform is to first address this interoperability and the people process aspect so that we can slot in advanced pets as we develop. And the idea is to work with any kind of data sets that organizations have in their own databases and provide it for different applications in a safe and secure way by integrating through the three personas that we mentioned earlier, which are quite generic across organizations. And this was done through quite intense interviewing. And maybe before closing, I'll just highlight just one aspect on the right corner, which is watermarks. If you have recently viewed Google's I/O or even OpenAI talking about watermarking their outputs, we have been doing watermarking. So any data set that goes from Privitar, that goes through Privitar to any application, is automatically watermarked. And if the data set gets misplaced anywhere, you can trace it back to what purpose the data set was given for and to whom. So maybe I'll close there and take questions. Thank you.